Anyway, well, so we're all here. We're ready to go. I'm Sandy Pentland here at MIT, sort of one of the members of IDE. And we're going to talk about machine learning. And then in the discussion, I think we're going to get off into ethics and practicalities of using it. And to kick us off, we have two short talks, one about machine learning. And of course, we've got to estimate heterogeneous treatment effects. So I have Jas Sekhon from Berkeley to talk first. And then second, machine learning choices. And we have Johan Ugander from Stanford for that. So Jas, you want to kick us off here?
Sure, thanks.
Oops. Here's the control.
Yeah, thanks. This is a wonderful conference. Thanks, Sandy, Sinan, Eric. This is like great. I love the format. I like the audience. This is great. It's my first year here, and I greatly appreciate it. It's awesome. I've learned a lot from everyone. So I'm going to continue the theme of not letting a session go by where we don't talk about heterogeneous treatment effects. The cool thing about this audience is I don't quite have to motivate. The heterogeneous treatment effects are very important, and we need to estimate them. I'm going to mostly talk about there's difficulties with their estimation, and some of them are subtle. I'm going to point out some theoretical results. One of them, I think, has a lot of practical implications. The other one that we just did doesn't have a lot of practical implications. I should have mentioned, this is joint work with my colleagues at Berkeley, Peter Bickel, Bin Yu, and a grad student of ours, Soren. So that's going to be the flow of this. And because I'm going to talk about the problems with estimating heterogeneous treatment effects, I want to first say, I think it's a very important thing to do. So I want to give like two simple examples. The first one is a medical one because it focuses the mind. This is an experiment whose analysis I was involved in. There's a thing called pulmonary arterial catheterization. It monitors blood flow in your heart. People in the ICU are critically ill get this often if people are worried they're going to have a heart attack. And this thing, like many medical interventions instead of drugs, was first approved without any randomized controlled trials. And then finally, after a series of observational studies which showed that this thing killed people, they finally did a randomized trial in Britain, and they called it the greatest name ever for a randomized trial, the Pac-Man trial. And the Pac-Man trial showed a zero treatment effect. The point estimate was even a little negative for in-hospital mortality, and then they basically stopped funding it. The only problem was, as you can see, there's a lot of heterogeneity. This is like a density plot of estimates of individual treatment effects. It's really conditional average treatment effects for every individual. And you can see some people have positive effects, some people have negative effects. If you just do a subgroup analysis defined by subgroups that physicians thought it might help, before you find the same thing here. The experiment wasn't powered to pick them up, but if you throw machine learning at it to get variance reduction, you can pick up this heterogeneous treatment effect. So if you're a regulator, you probably shouldn't have just pulled it off and probably would have asked people to target it better. It's a political campaign, and I'm doing lots of political experiments, which I can't talk about. So I'll talk about a political one that I can't. So this famous study came out about 2 years ago in Science that many of you may have heard of, that if you knock on people's doors and you talk to them about gay marriage, you can change their views on gay marriage even months later. It turned out to be all fraud. So two graduate students of mine, David Brockman and Josh Kalla. David Brockman's now a professor at Stanford GSB. They actually did the study with the LGBT Center of LA. The study was done in Miami, and this was reducing transphobia, because that was the issue. And they found a significant and lasting treatment effect on conversations reducing transphobia. Now, unlike the previous study, when they looked at subgroups, when they used linear models, they couldn't find heterogeneous treatment effects, right? And that's what's reported in the Science article. If you throw a big machine learning algorithm on it, you find significant heterogeneous treatment effects. So this is a question of, wow, my simple subgroup analysis doesn't find it, a linear model doesn't find it, but if I go non-parametric enough and I throw enough machinery at it, I do find it. So now I should kind of I have a question, do I really believe what I just did? Right? And these differences so some subgroups have a negative treatment effect and transfer, others have positive effects. So there's a decision to make. Right. So first, I just want to walk through. I'm going to just put in a little bit of notation because I want to talk through a thought experiment, and the thought experiment comes from some key results from information theory that I think tell us something very useful about estimating personalized treatment effects. So this notation showed up in a whole bunch of talks yesterday. So the individual treatment effect is just defined as the difference between the two potential outcomes. So call that D sub I, and our estimator for that, call it tau hat sub I, right? And then we just want to estimate the average of that within like strata of X, if X is like discrete. So this is like something that we've seen many, many talks, right? So let's decompose the mean squared error of that, right? And this comes up, this shows up in some papers and then quickly ignored, often doesn't show up in papers at all. The mean squared error of that conditional average treatment effect is of two components. The first component in red, we ignore. The first component is the difference between the conditional average treatment effect at X and your individual level treatment effect, right? So if I've stratified on just gender, right, just one covariate, right, that first term is going to be my residual relative to the average effect for all men, right? And that doesn't go away asymptotically. I have an infinite amount of data. That residual is still massive, right? And we just ignore it. We say, all right, we don't know what to do about that. But that's personalization. The second part is what we can do. Oh, yeah, I can get the average for men right asymptotically, right? And all our theorems that we have confidence intervals for the conditional average treatment effect, they're all about that. But in a profound way, by definition, that's not personalization. We ignore the other part, right? And that has like some issue, and I'll give you a little thought experiment that comes from decision theory, and I'm going to state it in terms of the normal distribution and expected loss, but the result goes through for almost any distribution and any loss function. It's just got to be like a negative definite kernel, but we'll just do it all in normal, right? So imagine there's a normal distribution, right? And it has mean, mu, and variance sigma squared, right? And we're going to play a game. You're going to predict what the value of the next yi is. You're going to think about it as the next treatment effect is. And you guys are lucky. You get an infinite amount of data to learn this process, to make that prediction. I only get one data point. So you get an infinite amount of data, you get big data. I get one data point. How much better do you do than me on expected risk? Expected risk is your guess, is the expectation of your guess minus the true y high squared, right? And it turns out that you only will do twice as better than me. You have an infinite amount of data. I got one draw. You're only going to do twice as better than me. Your expected risk is going to be sigma squared, right? Because you learn this distribution very well. You learn mu, you learn sigma squared, you take a guess of mu, your expected risk by definition is sigma squared. I'm going to get 2 sigma squared in expectation. I got one data point, right? Which says that if I'm going to predict someone, a whole bunch of data doesn't help me much. You have an infinite amount of data, I got one, you're going to do twice as better. What I got to do is I got to reduce this sigma squared. This is the essential heterogeneity. So and this happens when people ask me to do heterogeneous treatment effects, and they said, I can give you 1 million observations. The first question is, how many covariates do you have? Right? I need granular information on people. I need dimensionality on K. Like K being the number of covariates, that's way more important. Right? If I want to know what the causal effect for Sekhon is in some medical thing, in some ad thing, in some get out the vote thing, way more important than getting 1 million observations is getting the prognostically important variables for Sekhon and get someone close to him in space, right? And that's way more, and I gain way more from that than I do if I got like infinite amount of data on like one covariate, right? And that's just like it's a somewhat surprising thing. The first part of it isn't surprising. The second part is the generality of the theoretical result is not surprising. It's not our result. This result is it's been kicking around information theory for a while. No one's noticed that it has like this implication for causal inference. Right? So the first thing to note is most of what we do about personalization is not actually that. We ignore that part and we do this subgroup thing, right? So then we have another set of results, right? And for the other set of results, we're going to stay at a very high level, and we're going to define a bunch of learners. And the way you do estimation can be any which way. You can do estimation by regression. You can do it by k nearest neighbors. You can do it by random forests. You can do it by neural nets. We don't care. We want to define some high-level things, right? And one of these learners we're going to call the X learner I'm going to define. I'll just, for the purpose of this talk, just define 2 more called the S learner and T learner, and I'll define what they are. So for the X learner, right, it's going to like estimate a bunch of things, going to give you a treatment effect. It's going to have an advantage that you're going to estimate the models for your outcomes separately from the models of the treatment effect. That's sometimes going to be an advantage, sometimes not. Somewhat more interestingly, what we do is we provide minimax lower bound results for if you want to estimate the conditional average treatment effect over a class of distributions. And what we show is that all these learners achieve this optimal rate. Now, they may not all achieve it, but they perform very, very, very differently in finite samples. And by finite samples, I mean you have 1 million observations and 1,000 covariates, right? Which is not that finite. So now, like, the theory isn't really helping you that much. It's what's like taking so long for us to generate these papers. We actually want to get theory that's useful for practice, right? But this should be a big cautionary tale, right? So here's one learner, right? Here's our X learner, which sometimes performs well, sometimes not so well. But so let's think through and walk through this a little bit. And this is, so one thing you do is you estimate a model for your controls. You estimate a model for your treated, right? And that becomes the mu0 and the mu1. And then you compute residuals, right? Because I know what your outcome under treated was, because you observed that. I take my model for controls, and then I impute your control outcome. For the other group, I know what you did in control. I take my outcome of treated and I impute your treated outcome. But now I have two different ways I could estimate the conditional average treatment effect. One is from the first model, right, where I've observed treated and I've imputed control, and the other one where I've observed control and imputed treated. So I get those, tau hat 1, tau hat 2. Then I can like average those, and we average them by the propensity score, right? Now the key feature this thing has, and this won't be alone, is that when we go to data, the covariates that we do that predict y0 and y1 are usually way better than the ones that predict the treatment effect, right? And the reason for that is obvious. I don't know anything. If someone says, I want to study X, and I have some experiment I'm going to run, and I want to collect some covariates, what am I going to say? I'm going to say, collect the lag value. Because the lag value is usually going to predict the outcome quite well. Right? So it's not like a miracle that in the two experiments, for example, I showed you, you have R squareds, like very high R squares. Like the transphobia one was like 0.8. I can predict the outcome. If you ask, okay, what's the R squared on regressing tau on the outcomes, on the baseline covariates, it's way, way lower. Because, well, how do I predict the treatment effect? Do I get lag tau? Well, no, I don't usually have the lag treatment effect. Right? So it's going to like take the fact that on one hand, it's going to do the maximized reduction for variance, because it's going to model y, and the other hand, it's going to model tau. It's not always going to be the best. It's going to sometimes not be so good. So then there's two simpler versions that have been used in the literature. One is called, like, say, the t-learner, which is I'm going to estimate a model, and I don't care how random forest, regressions, for vector machines, do your favorite thing. On the controls, one on the treated, and you just take the difference. Right? That seems to make a lot of sense. And the other one is even the simplest model, which is, okay, I'm just going to like put everything in the soup, including treatment, and let the learner figure it out. Right? Put treatment as just another variable in regression, support vector machines, random forests, have your heart's content. What's going to happen is there's conditions in which, although these things all asymptotic should be the same, that one of these will dominate the other, and these choices don't go away. Right? And all these are black box. I can turn any black box machine learning algorithm into a causal inference algorithm doing this under, you have a randomized experiment, but these big choices are going to matter. So intuitively, to think about why you might want to do this separately is that imagine you just saw these data points and these were treated data points, right? And you're going to like, all right, this is my treated data points. How am I going to fit a line? What kind of function am I going to fit through it? I don't got a lot. It looks pretty linear. So maybe I'm going to fit a linear model through it. Right? It's really hard to motivate anything but a linear model. Say I see these control observations. I have many, many more. And you're like, oh, wow, OK, this is pretty complicated. It looks like there's a step function. So I'm going to estimate like a step function there. Right? And if you do that, which is what, like, say, the t-learner would do, and which is one of the things people use to estimate conditional average treatment effects, you're going to get into a problem. Yes? Oh, sorry, 5 minutes. OK, sorry. Sorry, Sandy. It's early in the morning for me. So if you estimate, so you can estimate like a step function of the controls, a straight line for the treated. And if you do the t-learner, you're just going to like take the difference, which is going to give you exactly the wrong answer, right? Because in this case, the treatment effect is 1 for every unit, right? And then if you do like the x-learner, what you're going to do is you're going to take this residuals, and then you're going to estimate the model for tau, and then you're going to learn that it's that almost straight line, right? And the t-learner, if I split the data in treatment and control, and take a difference, so I'm going to estimate the step function, which is going to be like exactly wrong. Now, asymptotically, this problem will go away, because asymptotically what's going to happen is you're going to get plenty of blue points. And as you get plenty of blue points, you're going to say, oh, it should be an estimate, a step function. But in finite samples, you're going to be terribly misled if you don't like also estimate the model for tau. Unfortunately, this problem, in this case, the x-learner will do much, much better. This is not a general result. This figure is like a little hard to see, a little harder than I even thought. The key thing to learn is like, so the blue line is the x-learner, the green line is I'm going to estimate treatment control separately, the t-learner, and the red line is the s-learner, like I all do it in one go. And the key thing to learn is one of them is never the best, right? And so like if the treatment effect is constant, right? It's 0 or 1 or 2 or 3. Then intuitively, as you should think, the S learner is going to do the best because it's going to pool Y0 and Y1. And that's exactly the right thing to do, right? And it does the best, and then the T learner, the one that splits them, does the worst, right? In the case, however, like say, like you're going to estimate the Causal effect, and it's really complicated. It's very rough, right? Then you're going to like not want to like do the X learner, because then the T learner is going to do better, right? And then there's going to be cases where there's nothing similar between treatment and control, right? Which is going to be in this bottom right-hand corner, and the S learner does terribly, right? In the sense that treatment and control are very, very different, and then if I start pooling them, I'm going to get a lot of errors and problems doing that. So like the details don't really matter. The things to note is that our results are pretty weak, but all these things should hit this optimal convergence rate, and yet they behave very, very differently in finite samples, even though the finite samples are quite large, right? And this is part of why it's been hard for us to like move progress on this. If you're willing to make some assumptions, you can get clear theoretical results. If you're willing to say, for example, that your treatment effect model is sparse and linear, but the underlying models can be like super complicated, then like we could derive an estimator that's going to be more efficient than any of these, and it's going to be more stable. And that has some issues, because the other thing that worries me really, it doesn't really worry me if this is a recommendation system. It doesn't even quite worry me if it's election campaigns. It really worries me in the medical case. Or it does worry me if it's about who gets credit or who gets housing, in the sense that the confidence intervals for these things are like really bad, even in relatively large samples, right? And if it's a really simple, and this is like the top, is like, this is the coverage of these estimators as the dimensions get large, as you have 5 covariates, 20 covariates, 100 covariates, and I think this is for 10,000 observations, but even at 10,000, the coverage you're getting at 100 covariates is like 0.25, and you ask for 95% coverage, right? They're just atrociously awful. I mean, the theorems work. That is, this goes to asymptopia. This does work out, but in the long run, we're all kind of dead. So if the stakes are high and you really got to make the right decision, you might want to revert back to like subgroup analysis or simpler models. Our variance estimates are a little delicate right now, and by we I mean like all of ours. Unless in very simple cases, then it works just really fine. If we just say the conditional treatment effect is just 0, or it's constant, or it's not that moving, then you just nail coverage very, very well. And so there's a tendency often not to like come up with the most critical simulations you can for your own estimator, right? So so we got to do more theoretical work, which we are, and this is like also like one of the uplifting things about where we are in the modern age. Of 10 years ago, if I think we've written this paper, we'd have just written the theory and called it a day. But now we have data, we have simulations at scale, and now we actually ask something from the theory that you didn't historically have to ask. And one of my colleagues, Peter Bickel invented semi-parametric theory, and he chuckles at this. And it's like, yeah, now you're asked to like actually perform well, and and that's useful, but it's difficult. All right, thanks.
Thank you. Very cool. So second speaker here is Johan Ugander from Stanford, and he's going to talk about machine learning choices.
Great. So this is discussing very recent joint work with a new graduate student, Stephen Reagan at Stanford. And it's based on a paper that the main contribution of this talk is a paper that's coming out at NIPS, which is a machine learning conference in December. So the starting point for this talk is a problem that I think a lot of people in this room have a lot of experience with, which is this classic problem of predicting discrete choices. So you're trying to predict which of these ice creams a consumer wants, or with what probability they want different ice creams. Or you also have the classic problems that have been studied with this framework include choices of transportation options, particularly in the Bay Area. We have some new options now. And BART is still around. And then there's also this problem of school choice, and sort of whether also the choice of school versus the choice of work, and questions like that that are core to the history of this problem. As many people in this room know, there's kind of a new version of this problem that's ubiquitous in online settings that has way, way more data. So if you're Amazon, you're trying to decide what items to recommend sort of in a recommendation system, you're trying to really you're trying to suggest items that are very likely to be chosen to show next to an item, or you're Spotify and you're trying to compose radio stations, you're Google and you're trying to complete search results for digital cameras, or you're New York Times and you're trying to piece together which articles to show. And there's been a whole lot of work in machine learning on ranking items, but what I'm kind of going to talk about in this talk is kind of this movement from a framework of learning to rank to sort of focusing on the difference between ranking and choice and talking more about learning to choose as the right starting point for some types of questions. So the real catchphrase for what I'm talking about is the presence of choice set effects, which is also the violation of the independence of relevant alternatives that a lot of people in this room have probably a mouthful that's familiar to many people. And there are these have many shapes and sizes, and sort of behavioral economists have given us a kind of a battery of different effects that they've been able to identify in a bunch of scenarios. So we have decoy effects, asymmetric dominance, bias towards moderation. Somebody once told me something called the leather jacket effect, and I said, OK. But the real question here is, can we present some framework that sort of learns the presence or absence of these effects in a generic setting where we don't know, oh, yes, OK, we have this kind of just so story of why this one effect is going to matter. Can we learn the presence of these effects generically, or kind of any and all of them, or which of them and which not of them? So the starting point for a lot of this dates back to sort of Thurstone's psychometric work on learning from comparisons. So I'm kind of going to build this up and then show you how what I'm thinking about these days is different than that. So there's this classic question of which of these two digital cameras do you prefer? And you say, OK, I prefer the one on the left. Great. And what you can do is you can start building kind of a directed graph of choices between alternatives. You ask another question, which of these two different cameras do you prefer? I prefer that one. Which of these two cameras do you prefer? I prefer this one. And over time, you eventually have kind of this pairwise comparisons. And this problem is sometimes then turned into this question of ranking from comparisons. And really, what you're doing is you're taking all this data, pairwise choices, and you're running some kind of maximum likelihood procedure to learn a latent embedding or some kind of quality measure that comes out of the Thurstone measure, and Thurstone model, case 5, and then also the Bradley-Terry-Luce, Plackett-Luce. All these models kind of have they're closely related in this literature. And really, you're trying to kind of learn where in this kind of latent dimension of quality do these items live, and you're modeling choices as kind of, there's these distributions that are yellow, green, purple, et cetera, for these different cameras, and the probability of choosing A over B is the probability of getting a larger draw from XA than from XB. And so this is a classic approach to the problem, and then it generalizes to choices from larger sets. So instead of just doing pairwise comparisons, you have these setwise choices, and you have general random utility models, and largely this is solved and can kind of be called like the multinomial logit model of discrete choice. So this is standard solutions to the problem, and then also folds into kind of this big literature of machine learning that came up in the 2000s, which is learning to rank. So this great starting point for Google was PageRank, which let them give kind of a good first try of how to rank the web. And then what's really happened after 2000 is that was really kind of a decoy that was put forward for how to figure out how people click. So once they kind of were presenting search results based on PageRank for a while, they then realized that actually you have this much more informative signal, which is all of the click logs of how when people search for certain things, what do they click on. And nowadays, since at least the early 2000s, PageRank is just a feature of a giant sort of learning problem of how to rank search results. And there's a whole literature on this based on pairwise methods, listwise methods, pointwise methods. And there's lots of experimentation challenges here where, so a classic one is that you're only observing things in the order that you present them. So how do you need to do some kind of exploration instead of exploitation in order to identify things like position effects. But in general, this works very well. But this is what I want to get beyond with this talk. So I want to talk about this problem of kind of learning to choose as something different than learning to rank. Because there are these basic assumptions that go into ranking. The first one is kind of this basic idea that you have some amount of transitivity. So if I'm picking A over B and I'm picking B over C, that says that I should be picking A over C more likely than not in each of those cases. You also have these properties like regularity, which says that if I add something to a set, the probability shouldn't go up. The probability of choosing one of the items in the set that I added to shouldn't go up. So I can't increase the probability of choosing something by adding other things to the set. And that's kind of the core of this. Like you're independent of irrelevant alternatives. There's irrelevant alternatives that you can't add those and change things. And that's another way of writing it then is the independence of irrelevant alternatives, aka choice set effect, which basically says that the probability of choosing A from S and B from S is kind of, this is one way to write the independence of irrelevant alternatives. So these assumptions are all core to how a lot of these ranking problems work. And there's been this recent burst of work in machine learning on how to get beyond this independence for irrelevant alternatives. One of the more sort of, a well-written title is this, and it's also a good paper. Austin Benson, Ravi Kumar, and Andrew Tompkins at Google have this paper called On the Relevance of Irrelevant Alternatives, which is a big measurement paper where they go through a bunch of decision flows of users at Google who are choosing restaurants and listening to music, and kind of documenting the fact that this assumption does not hold across a bunch of constructed examples of kind of sequential browsing. It also has received attention in the literature, unsurprisingly, on ad quality. So there's this work on ad group quality, kind of the idea that you can increase the click-through rate of an entire ad bundle based on what ads you put into that bundle. Which is also sort of very productive. And basically, the web is full of these violations of IIA. So there's this, now I'm going to talk about this kind of like new eyes on an old problem type of thing that's been going on very, very recently in the last, at most 5 years, but a lot happening in the last year. So learning these models there was this connection that was made in a paper last year that basically, I laid things out as you can turn this pairwise comparison data into a model by solving a maximum likelihood problem. And there's this paper at NIPS last year which makes this observation that actually an equivalent way of learning this embedding is to do a random walk on the choice graph. So you take these items, you have this graph on the left-hand side, and you do a random walk, and you look at the stationary distribution of that random walk. It's a continuous time random walk, and there are details of how you set up this random walk. But actually, they put this forward as kind of an algorithmic contribution. They say instead of maximizing this likelihood where you can use convex procedures for convex objectives, you actually just do this kind of spectral technique, this random walk-based technique, and you can compute the same embedding 5 to 50 times faster for large data. OK, great. This audience usually isn't that interested in kind of faster methods. Most of our stuff, or actually, you probably are, but we're not mostly here talking about research on faster methods. What's interesting about this observation is that what they were actually saying was that the stationary conditions of a particular algorithm that's maximizing the likelihood are the stationary conditions of the following Markov chain if you set it up in the following specific way. So they said, consider a pairwise Markov chain where here you have your digital cameras, and the rate of transitioning from camera 1 to camera 2 is this ratio of the kind of the BTL qualities. And so pairwise, you're kind of jumping back and forth with sort of a rate that's like the quality in one way and the quality in the other way kind of normalized. And you do this pairwise for all the items, and it actually turns out that the stationary distribution of this Markov chain are these latent qualities. So you can learn these latent qualities from that chain, and it's sort of great algorithmic contribution. But what I'm talking about now is the fact that there's a way in which this analysis suggests a much more general choice model, which is that we don't need to stick to this really narrow characterization. So basically, there's a more general Markov chain here where a special case reproduces MNL. And so what I'm going to talk about is that modeling these discrete choices using this more general framework, all of a sudden we now have this model that's really usefully flexible for modeling these not as rational behavior in human web users. So the basic summary of what's going on is that we model choices from a pair by just this kind of these rates of Q1 and Q2 between two elements. So if the thicker arrows denote larger transition rates, we would see this Markov chain on two items and kind of end up, that model would have a stationary distribution where we would be picking the red camera more often than the black camera. And then when we move to something like 3 items, we would add another item. And maybe because there's really strong flow from the red camera to this third camera, we actually end up totally changing the stationary distribution in a way that kind of models this kind of interference effect or this kind of violation of IIA, where you add that purple camera in, and it kind of steals choice from the red camera to the black camera. And so you end up having order n squared parameters. I'm going to get rid of those in a second. You'll get that down to n. And in this way, you kind of learn choices and predict choices really well. So what's going on with this model before I give kind of prediction results? It's not assuming even regularity. So it's not a random utility model. And if you kind of are up on your choice theory, even Tversky's elimination by aspects is a RUM. So this is like a very general model. And you almost should be afraid that it's too general, that it kind of has no structure, that you're learning an arbitrary mapping from items to sets to items. But we actually have this funny axiom that turns out to give a lot of structure. So we're satisfying something called uniform expansion, which comes out of the choice theory literature in the 70s, which is this thought experiment where if you have coffee, tea, and milk, you're just as likely to pick coffee from the set coffee, tea, milk as you are to pick some version of coffee from 100 copies of coffee, 100 copies of tea, 100 copies of milk. So you go to the table back there, and the relative probability of picking coffee, tea, milk shouldn't depend on how many copies of coffee, copies of tea, copies of milk there are in the back. It's more general than IIA, it turns out. But it can be shown to imply Luce's axiom under a independent RUM structure. Happy to talk about that offline. So we have this axiom. And we actually generalized it as something we call contractibility, which relates to a thought experiment by De Bruyne that I can go into some other time. But basically, we do have, this isn't a structureless, it's usefully lacking some structure, but it's not structureless. And then when we go to data, so here's a funny thing. This type of data is really hard to get out of large companies in a way that you can share the data. So the main data that we're validating on is actually sort of the old school choice theory data, transportation decisions. And so this is transportation decisions around the SF Bay. And for work trips data and shopping trip data, we're doing something like 20 to 30% better than an MNL. And we're doing 15 to 20% better than a mixed multinomial logit, which is sort of still a very flexible model. And so, and this is, sorry, the x-axis here is how much data we're giving our model. So we're kind of giving it more and more data, and then we're predicting out of sample on kind of a holdout. And we're the blue line, and we're like winning, et cetera. This classic horse race plot. So we're doing 20 to 30% better. And an interesting property of this model is that if you have IIA, then this model reduces to MNL. So if you were to employ if you run this model on data generated from a multinomial logit, you just do as well as multinomial logit. You have a little bit less statistical efficiency as you're learning because you have more parameters, but you basically you're kind of lagging it, but you have the same rate of learning. So you can also interpret these models by looking at their parameter matrix is actually a pairwise probability matrix. So you can break this down and say, here's this pairwise probability matrix where I can now try and interpret, on the full set of 8 items in the transportation, or 6 items, the transportation options, what are the kind of pairwise choice probabilities that bubble up to form the aggregate prediction. And there is lots of non-transitivity that I won't go into. Now, I previewed this point that there's actually very clean ways to parameterize this matrix with just order n parameters, which is based on also very recent work, 2 papers in the last year by Shu Chen and Torsten Jochims. Something called a blade chess model, which is kind of an embedding model that's interesting for non-transitive comparisons. But the big picture that I want to take away here is that we talk about all these designed online systems and social systems, and there's kind of like, there's a slew of questions that are on the horizon that I find to be really interesting. So there's questions like testing, do choice set effects exist? Choice set effects exist, and if so, which ones? I don't know anything about learning bounds and sort of theory questions for this model. There's this design question of, given x, what s should you show it in to maximize x? Now that we have this kind of way of learning these models, how do you do that? There's also the things that bubble up to bigger ethics questions, like if we're predicting choice set effects, do they go away if we explain to somebody, actually, you're being crazy here because you're just getting caught by this one decoy, et cetera? What's the user experience research around that question? We're actually not incorporating covariates, so that's sort of ongoing work, and I know how to do that. I just haven't gotten there. And then there's also this question of moving from learning to rank to learning to choose, and then the joke is choosing to rank, which is the idea that can you place distributions over permutations that aren't centered around well-ordered structures. The biggest questions that come out of this is this point that there's actually divergence between artificial human intelligence and artificial intelligence. This is models that are modeling human bias, really, that we're trying to exploit, and sort of what does that mean, and why should we be doing that, or what are the returns on that? And then this other question about sort of the ethics of libertarian paternalism or maternalism with respect to the fact that we now know how to design these systems. Should we be doing it, et cetera? So thank you.
Don't go away. Go back. Come back. You too. OK, good. So a couple of great talks. Let's get people up here, and then we can chat about all of this. So let's go to some of the bigger picture things to sort of start with, but later we'll sort of open it up. Soon we'll open it up, and you can feel free to ask sort of general interest detail questions if you want. So one of the things that we had talked about beforehand was sort of the ethics of designing these systems, sort of doing nudges and things like that, where you're trying to use people's unthinking patterns or less than fully rational behavior to be able to move them in a particular direction. And so that has this sort of, the AIs are in control of your mind type of flavor to it. So maybe you can comment about those two, both of you. You wanna, since you suggested that once.
Yeah. So yeah, I'll make the connection. Jas and I were talking about this earlier, or I'll only say what things I'll say. But there's an interesting connection here, which is I haven't at all thought about heterogeneous treatment effects, and I apologize. And for this problem, I've thought about it in a bunch of other cases. But and if you apply these type of models and you learn that you know how to kind of fool men but not fool women, now you're kind of in this personalized version of the libertarian paternalism problem, which is how ethical is it to kind of be taking action on this ability to fool or kind of know a better interest of these individuals at a personalized level. And that gets really complicated. Fortunately, Jas tells us that we don't know how to do that, or we can't do that. But I think that's like a level up on like the difficulty of a lot of these ethics questions.
Yeah. So it's difficult. It's not that we can't do it. It's just like there's this noise that sits there. I mean, it's gonna like happen, right? Like the people that we have better prognostic variables on, we're gonna get better predictions on, right? Even if I don't know how to predict the causal, the conditional average treatment effect that well, if I could just predict your Y outcome better because you're online more and I have better data for you, that's gonna then imply a reduction in the variance of all my estimates. So you're gonna get your interest better served to the extent that the ad platform serves your interest, right? I would like my interest. I mean, I want the ad platform to give me ads on exactly what I want, right? So if you don't have good covariates on me, you're going to do worse on me. And that has like some implications because we have better data on some people than others. And whether that's good or bad sort of depends on, is the algorithm on the other side serving your interest or not? And that gets complicated because we can disagree. Like to take the example from last evening in the fireside chat, the STEM experiment, and then women got it at much lower rates than men because women's eyeballs are more expensive. Like that could be read as two ways. I goes, oh, if your eyeballs are more expensive, you're seeing better ads. This is great. So yeah, you didn't see the STEM ad because you weren't willing to pay enough, right? But on average, the higher payers should be better. But maybe that's not true. You can easily write down a model where that doesn't sort of happen. So to get from like the statistical issues we point out to the ethics is like many steps. And
so something that's this point that recommendation systems have a useful like predictive role and sort of but experiment, and there's been a lot of work on that and sort of what is the interface jump from there to causality. I think that an interesting question there, or a difficult problem that I've thought about before, is this problem of if you want to try and run an experiment over advertising these days, the systems are doing such a good job of customizing who the audience of the ads that are being shown. For example, the example given yesterday that male eyeballs are cheaper. You can't just take two creatives and ask, I want to check the effect of There was a talk yesterday about putting babies on a website and seeing the effect of that. If you want to do that in ads in Google, you actually have to, it's going to learn the fact that different people respond better to the baby, and it's going to be showing your ad to different populations. And now you're kind of have to think about that really carefully before you look at the difference between the two treatments. And so these systems that are doing a great job of learning are really I've asked people like at Google Research New York, like, how can I control for this? And they were like, you kind of need us to put our finger on the scale. Because running experiments on top of these systems is really hard, for sure. Yeah.
This is like a huge, so right now my head's on elections, doing election stuff. If you would say you're a campaign, you want to spend your marginal dollar on what platform, to get an experimental estimate out that's credible is like amazingly difficult. And one of the things that these systems are doing, which relates to heterogeneity, even if there is no heterogeneous treatment effect, the systems are inducing one in the sense that people are endogenously selecting the control they get, right? In the sense that, because they're not choosing, but the algorithm is, but it's kind of like an endogenous selection, right? If you don't see my ad, you're going to see what the system thinks is an ad you're going to like. And yours might be different than yours, they might be different than yours, such that if I can get the A-B comparison, I might have a homogeneous treatment effect, but I'm not observing that in the data. This is like the cynic in me says, you have this huge industry, we talk about innovation, and I'll repeat, we see innovation everywhere but in the productivity numbers. And then if someone asks a simple question, can you show me what the ad effective, what is the lift? What is the return on investment for like a major political campaign? It's a very hard question, right? And like 10 seconds.
So the part that bothers me about this, right, is that we have this big hammer, which are these ways of sort of modeling these things. And then we're making assertions about the people, okay? But in fact, one of the problems, like for instance, one of the things that's wrong or difficult about heterogeneous treatment effects is that you don't actually know what the people are doing. In other words, you don't have a causal model. If you had a causal model, you could try and solve for the parameters of the causal model. Instead, what we've got is models that are essentially piecewise continuous polynomials. And that's not people. And so by treating people that way, you are, by using that as your set of modeling functions, it seems like you're, well, to put it in an extreme way, you're dehumanizing people, but it's implicitly talking about the range of behavior that people can show. I mean, what do you think about that? Right?
I couldn't agree more. And this is like, look, I like heterogeneous treatment effects. If you're going to do anything like run a campaign, you're going to have to pick who to target and who not to target. But you're going to be aware of the vast amount of errors you make. Like if one says, oh, I have a personal system, and it's going to be like something that's like a medical trial or something, it's credit, things that we really care about, and you really want to take the word personal seriously, then there's like that personal variance I mentioned, right? And you can set up simulations to say, all right, does your thing recover correct coverage, and what's the mean squared error on that on individual person effects? None of this machinery is set up for that. That's not what the analytics are set up for that. And MDs get it, like I do some like medical stuff, and they get it, and they say, well, look, you're giving me for subgroups. It's also all fancy now, but it's still like kind of like subgroups, right? And it's not like the person. And all too often, the statistician pushes back and says, oh, you MDs, you just don't know. You didn't take real analysis. If you did, you would know. And no, they're like, no, they're actually making a core point that you can't dodge, and it has this ethical thing that if your ethical defense is going to be, oh, I'm not discriminating, I'm not making a bad thing, I just a really good predictor for you, your defense can't be you estimate the conditional average treatment effect well. It has to be, all right, tell me what that person's error rate is. Oh, that's a difficult question to even pose clearly. But that's what the person's going to ask, not.
I also like your point that you made about the sort of that there's very sparse parts of the space where there might not be people like Sinan. He's a very unique character. And to what extent, there are certain people that you then, if that's what's driving sort of lots of proximity in the larger and larger covariate space, how should we be thinking of, tying up to these questions of ethics, like how should we be thinking about oversampling hard-to-reach populations into those types of data sets, et cetera? I think that's hard.
So a related question here is, you mentioned human AI or modeling bias, right? And we just talked a little bit about what are the sort of causal mechanisms. A common theme that comes up sort of at the edges of economics is we see these paradoxical effects in human performance, but sometimes it's because the people are solving a different problem than the one we think that they're solving. We set something up that says, well, we're going to maximize the utility defined as dollars per unit, whatever, and the people are actually doing something quite different, and we just don't realize that. So things that look irrational are actually a function of having a different utility function, and that gets back to this question about values. What do you think about that? So, because another thing that we sort of jump in without thinking about a lot is the utility function, the values in there.
Yeah, I mean, that one and your first question, like there's kind of, there's a relation that when we do this, like we'll like, hey, look, we identify some effect, we're not going to estimate, we're not going to do structural estimation, and we're kind of like, we're not trying to hunt for latent things, the choice thing you are, but all too often we're not trying to claim that we observe, we're going to try to estimate latent things and get utilities. But without that, you get this problem of even can say, well, will this experiment be useful tomorrow? Or, how will it work? How do I think it's going to work for like the next individual in this group? I mean, all this stuff I think is kind of tied together that if you're not going to do the structural estimation, I generally don't, because it's like hard to validate. But a lot of the questions you're asking about people's utilities, how does it, can we theoretically characterize why the algorithm is doing what it's doing? Can we theoretically characterize how the treatment effect's working so we can figure out whether it is biased or not? All those things are then unanswerable, and that's unsatisfying. So we sort of like have to do the structural estimation, even though it's difficult and hard. But
yep.
My main way of viewing that stuff is that a lot of these systems, you're very much damned to mean what you say. So however you define the model, kind of these questions about artificial cars that we don't know which decision are they going to make to hit the pedestrian or hit the drive onto the sidewalk. It's kind of like there is a utility function defined by the code, and so you're kind of damned to mean that unless you specify it otherwise. So we are making a choice. I think that's interesting for a lot of these types of social systems, that they're ultimately kind of design systems, and there is no neutral option, and we need to kind of like think about the classic problem of A/B testing as like, well, the ethics of A/B testing will maybe, I mean, this is kind of maybe different from medicine, but where in medicine there kind of arguably is a default world and you're kind of intervening on it, but in a lot of design systems, there's like not running an A/B test is just A from an A/B test is like a classic view.
Folks from the audience want to say something? Yeah? Anybody have any questions? Yeah, Sinan.
Yeah, so I sort of feel like you just answered my question for the last 5 minutes, but maybe you didn't. So let me just ask it again. So this is a question for both of you, but it's based on Jas's talk. So it really does have to do with this, the external validity of these heterogeneous treatment effects. You have this variability in model performance that's in finite samples that's based, in some sense, on the structure of the heterogeneous treatment effects themselves. And in the digital world, you've got these long tail, as Sandy mentioned yesterday, you've got these long tail behaviors, which means you're seeing covariates, behavioral covariates for some people at a much higher rate than for other people. And at the same time, you've got the endogenous delivery of the treatments with the system that is sort of like we're just not even talking about, that exists on Facebook or Google or wherever it is. And so how do we talk about the external validity of these heterogeneous treatment effects? You started to get into structural modeling, just some sort of theoretical approach as a solution to this. But as we know, there's lots of limitations to the extrapolation of those, mathematical identification, the assumptions that go into those models and so on. Cross-validation obviously isn't a solution to this problem in the same sample. So what do we do?
So that's a great question. And this is like the upside of the modern age is we get new experimental data much quicker, right? And like for example, the transphobia experiment I mentioned, there's there's replications going on, the data's going to come in, and before that data's in, I want my predictions, the conditional average Schumann effect, in the box, right, in a pre-analysis plan. The new data comes in, and we'll see if it's there or not, right? And with digital experimentation systems, you can run the next experiment. But then the workflow then becomes very similar to like old style, what is the effect for subgroups? You do your complicated algorithm, you get some predictions based on covariates, and you get brand new experimental data to see how it works. Note again, what you're validating is the conditional average treatment effect, not the treatment effect for individuals, right? That's a harder one to validate or even think through. But I think it's like a huge thing. So like I think Edo's here in the audience, like we were talking about yesterday, it's like, well, in the old school statistics stuff, we would really want a pre-analysis plan for this, right?
David?
Yeah, so I wanted to get back to Johan's question at the end, so this kind of libertarian versus a paternalistic viewpoint. And it's a wonderful question. And let's say that we want to be paternalistic, right? It's not clear that we want to be that, but let's say for the purpose of the question that we do. The thing that seems to be very difficult here is that we have all these biases. The purpose of your work is to kind of recognize that we need to be a lot smarter about the way we model choice. Therefore, as we've known for a long time, there's no underlying utility function that in a consistent way explains the way we act. So economists like to talk about revealed preference versus latent preference, but if all we have is revealed, what is the latent that we want to get back to? So the question here is, maybe can we imagine a way over time to use the output of your work to then maybe back away from that and find like a latent rational utility model that is maximally consistent with that, and then where we build a system to be paternalistic with regard to that, or do we do something else? It seems very tricky to know what to do here.
So it's a great question. I think that there's this like letting go when you like drop the transitivity and things like that. You're kind of like letting go of that, and you're kind of crossing the Rubicon away from any kind of like utility representation, and trying to like lay paths on the other side of the Rubicon is this interesting challenge that we understand how to navigate. One of the things that I've thought about that I kind of alluded to in my talk was a lot of, so ranking in the statistical language can only be thought about as distributions over permutations. And a lot of the tools that we have in that world are also based off of sort of Mallow's models, which are distributions centered around well-ordered, like sort of single, completely ordered reference permutations, and then mixtures of that. But actually, there's an extension of this work that I'm working on now that's almost submitted, which is that you can actually turn a choice model into a multimodal. It kind of naturally induces a multimodal distribution in a way that you're not specifying the number of modes. This type of behavior actually, you can just kind of, basically you can run down a set repeatedly and get something that induces a distribution on permutations, like what is the likelihood of the different permutations. And that's even more complicated to sort of wrap your mind around something that's like there are multiple modes of sort of different orderings that are the likely thing. And then there's this taking that type of like weird distribution and trying to talk about it. You invariably want to talk about the sort of main mode or median or something like that. And that's kind of the now, oh, like shucks, I'm back. I found myself back on the wrong, like the other side, the starting side of the Rubicon. That is a river in Italy, right? Yeah, anyway. So that kind of means that the language we have for talking about these things is limited. We're so tempted to step back to these like completely ordered representations. And I think it's something that statistical machine learning has to kind of develop a language for very much, because I don't have concise representations for these things.
Yeah.
Yeah, really interesting work. Thinking about Johan's work, I was wondering how much of it might relate to actually the choice process, and whether even if there's sort of a consumer search process in place, maybe people could be rum, but they're using the information encoded there. But I had a question about the heterogeneous treatment effects that I think applies also to Johan's work, because there's a large choice of possible treatments. Each choice set is its own possible treatment. So what are we actually trying to learn in the case of heterogeneous treatment effects in applied work? So Jas, you were looking at things like mean squared error of the conditional average treatment effect, but when we have to make a decision, it's often something like, oh, I'm going to roll out the treatment to everyone that the effect is positive for, so that's the decision I have to make, and I care how much I get certain cases wrong. Or in other cases, I have a fixed budget, and I want to know, in the campaign work, who are the top 1,000 people to treat, and I want to know how well I'm doing compared with the optimal top 1,000 people to treat. And so maybe you can say a little bit about what the relevant loss functions are there, and whether that makes some of your results better or worse, and what happens when you have combinatorial numbers of treatments.
Great. That's a great question. Yeah, so like on the campaign side, and for a lot of like advertisers, you just want you want the order. Like say you've decided on a campaign, now you want the ordering, right? We didn't present them. The ordering doesn't look much better than the mean squared error ones. Like these estimators are disagreeing on the ordering way more than we would like. It gets harder if it's like, oh, I have like 3 different choices of treatments to give, and I want to choose which one to deploy to every different individual, right? And that's also in the campaign world what it is for a certain set, right? Like I have Ohio, people, you have some prediction people that are kind of movable, take that as fixed. You have a bunch of treatments you could give, which one to give. Now it looks worse than the ordering thing, because now I really care about the confidence intervals in which they are, because some of these treatments are not of equal cost. In the medical case, it's like really bad in the sense that I really need to like control the type 1 error rate. We spend millions of dollars in medicine because we want to control the type 1 error rate, and we want that known, right? And the last thing you want is some machine learner or statistician coming in saying, you know what, use my thing and I blow up your type 1 error rate that you spend millions of dollars to ensure. Right? And that's like one of the things that, and if it's really life and death, and certain not things that are life and death, I think have the same feature maybe credit, maybe whether you go to college, you really want the type 1 error rate. And that gets completely blown up. And I agree, like for the campaign, if I get the type 1 error rate wrong, if you're like doing this, rolling out an ad campaign, I don't really care. Right? I care more about the ordering. I care about that. It still doesn't look great, but for the type 1 error rate, it's like really bad because the confidence. So you said, like, again, some of these examples, you get like a 22% coverage on a 95% confidence interval.
I think a lot about the web design of the online health markets, where you have these, if you have tried to sign up for Obamacare, there's like ranking algorithms and things that are almost surely guiding people's decisions. And I wonder what types, are there machine learners at the keyboard who are just blowing up type 1, or I don't know what the error rate is there, but that's there are strong ethical implications for how healthcare.gov is designed.
So I also worry about the fact that all of this is within a relatively static framework. You talk about a utility function and a choice. And of course, what you actually want to do is people to change their utility functions so that they reach another state. And that's another whole sort of level of abstraction. But to get there, we need to have coffee. And I noticed that it's 10:30, and we should, thanks, speakers.